Okay, you asked for it. Here it is, the motorcycle merry-go-round problem. So here we've got a gigantic merry-go-round of mass big M and radius r. We've got a motorcycle of mass little m and initial velocity 0. The whole system has an omega naught equal to 0. So that means that the initial angular momentum is equal to 0. Now, sometime later, we've got the merry-go-round. We're going to call it the disk. We've got the disk moving with some omega that way. We are going to have the motorcycle itself moving with some omega this way. And what we know here is there's no net external torque on the system. The motorcycle and the merry-go-round have a force of friction between them, but that friction creates an internal torque, and the net external torque is 0. So we can say that angular momentum is conserved. Let's do one more thing, and let's say that big M is equal to 10 times the mass of the guy in the motorcycle. So we know L naught is equal to L final. The initial angular momentum of the motorcycle and the merry-go-round is 0, so that means that the final momentum has to be 0. So that means that L of the disk plus L of the motorcycle has to equal 0. So we've got negative L of the disk is equal to L of the motorcycle. So negative I disk omega disk is equal to I motorcycle omega motorcycle. So let's say that for argument's sake we're given omega disk. We want to find omega of the motorcycle. All right, so that's really easy to do. We've got negative I disk omega disk divided by I motorcycle is equal to omega of the motorcycle. So plugging in values, we have a solid disk, which is going to be negative 1/2 mr squared for its I, times omega of the disk. And it does look like here omega of the disk is going in the negative direction, so let's just go ahead and put a negative in there, divided by I for the motorcycle, point mass, so it's going to be little m times r squared, and that's going to equal omega of the motorcycle. Motorcycle is going in the positive direction, and so we are going to have a positive omega because the two negatives cancel out. So let's see, the r squareds go away, and we have 1/2 big M, which is, as we said, 10 times little m up here. So we've got half of 10 times little m times omega disk divided by little m is equal to omega for the motorcycle. So the m's cancel, and we've got 5, half of 10. So 5 times omega disk is omega for the motorcycle. It's important to say that these omegas are in reference to somebody standing on the ground or hovering above. So we would see the motorcycle be going in the counterclockwise direction at 5 times what the disk would be going around. And the relative omega for the motorcycle, if we were a person standing on the merry-go-round, we would see the motorcycle going at 6 times omega for the disk, because we would have to get the relative velocity. So there's the basics for that one. And we use conservation of momentum to find them. Actually, a more interesting question. This doesn't happen instantaneously. It happens over time. And so there's an alpha, there's an acceleration of the motorcycle, there's an acceleration of the disk. What causes those accelerations is the force of friction between the motorcycle and the disk. Not only that, the motorcyclist is going in a circle around the merry-go-round, so their friction there has to also be acting in towards the center to supply the centripetal force to keep him going in a circle. So the better question here is, what is the minimum coefficient of friction necessary for this nice little circus stunt that we have going here? And it's a little bit more instructive if we actually put some numbers to it. So let's say that the motorcycle, little m, has a mass of 200 kilograms, and the merry-go-round itself, the disc, that's big M, is going to be 2,000, so it's 10 times the mass of the motorcycle. Let's say that the radius of the disc is 10 meters. And let's go ahead and say that omega for the disc, after all is said and done, is 0.1 radians per second. And let's say that the time it takes for the motorcycle and the disc to get up to speed is 10 seconds. So that means omega for the motorcycle, as we calculated before, is 5 times omega for the disc, so he's going to be going at 0.5 radians per second. And I'm going to put a negative up here for omega for the disc because it was going in the negative direction. And so if we look at kind of a view from above for the motorcycle, we see that there needs to be a force of friction going this way that is accelerating him and causing the torque necessary to get his angular acceleration up. We also see that there needs to be a component of friction going in this way to give the motorcycle his centripetal force needed to go in a circle. So the actual force of static friction is going to be going at an angle, something like this. Alright, so we've got two equations here. We know that the sum of the forces acting on the motorcycle are going to equal. Let's just talk about the radial forces because we're going to take care of the tangential forces when we look at the torque. So this is just for going in towards the center, so that's going to be mv squared over r. And for the torque, so we've got the sum of the torques acting on the motorcycle is equal to I for the motorcycle times alpha. So the force that's causing the centripetal force here is going to be friction. So we've got Fs going in towards the center of the circle is equal to m, and this is V is going to be r times, this is capital R, omega, whole thing squared, divided by big R, I should have put on the bottom. And the force due to static friction then is going to be one of those r's cancel with one of these up here. So we've got the force of static friction going in towards the center is equal to mr omega squared. And over here on the torque side, we've got the sum of the torques is equal to I alpha, so the only torque that's acting, or the only force causing a torque on the motorcyclist is friction. So we have r times Fs is equal to little m r squared times alpha. Okay, so we've got one of these r's cancels one of these, and we have the force of friction. Let's say this is the tangential force of friction is equal to mr alpha. So for the circular component here, this omega, it's important to recognize, is not 0.5. It's going to be the relative omega. As if you were standing on the merry-go-round, you didn't realize you were in motion, you would see the motorcycle be going the relative velocity, which would be 0.5 plus 0.1. So this is going to be 0.6 radians per second. And the alpha here, let's see, the change in omega for the motorcycle was 0.5, and that happened in 10 seconds. So we're looking at 0.05 omega divided by 10. So it's going to be, alpha is going to be 0.05 radians per second squared. So plugging in numbers here, we've got the force of static friction going in towards the center is going to be the motorcycle's mass, which is 200 times 10 times 0.6 squared. Plugging that into the calculator, we have a force of static friction going in towards the center of 720 newtons. And over here, plugging in numbers, we've got 200 times 10 times 0.05, which gives us a value of 100 newtons going in towards the center. So let's take those to the next page. We've got a centripetal component going in at 720, and then we've got a tangential component going this way at 100. So root 720 squared plus 100 squared is going to give us about 727 newtons of frictional force. So that's Fs, and we wanted the coefficient. So this is mu times the normal force, which is mg in this case. So 727 divided by mg, which is 200 times 9.8, is equal to our coefficient. So 727 divided by the denominator gives us 0.37 is the minimum coefficient of static friction required to get this motorcycle to perform this stunt. And is it really all that fantastic? If we go back here, and the motorcycle is going at 0.5 radians per second, using the wormhole equation, 0.5 times 10, it's only going at 5 meters per second, which is about 10 miles an hour. This is not that fantastic of a trick, motorcycle going 10 miles an hour. Think about the motorcycle going faster than that, like 50 miles an hour. That would be pretty exciting. Go ahead and calculate the coefficient of friction on your own, but I came up with a coefficient of friction of something like 9.5 required for a trick like that. So a huge coefficient of friction, not possible at all. So there, you asked for it, there it is, and it's a fun little problem. Definitely could see something similar on an AP test. Somebody, instead of riding a motorcycle, could be walking at a certain speed. All right? See you later.